In the grand theater of the elements, some players command the stage with a quiet yet profound presence. Lithium is one such actor. It is the third element on the periodic table, a position that tells us much about its nature. With an atomic number of 3, it possesses 3 protons in its nucleus, and, in its neutral state, 3 electrons orbiting around it. This simple configuration places it at the very beginning of the alkali metals, a family known for its vigorous and often dramatic reactions. I recall my own youthful fascination with these metals, their eagerness to shed an electron making them the most reactive of all metallic elements. Lithium, in this regard, is no exception, holding its place as a cornerstone of modern technological progress. The secret to lithium's utility lies within its atomic structure. Its 3 electrons are arranged in 2 shells. 2 electrons fill the inner shell, held tightly to the nucleus. The third electron, however, resides alone in the outer shell. This lone wanderer, this valence electron, is not strongly bound. It is easily given away, transforming the lithium atom into a positively charged ion, Li+. This tendency to form ions is the very heart of its role in chemistry and, by extension, in the batteries that power our world. The drive to achieve a stable, full outer shell is a fundamental principle of chemistry, and for lithium, the easiest path is to lose 1 electron, making it exceptionally reactive. This inherent reactivity is complemented by its remarkable physical properties. Lithium holds the distinction of being the least dense of all solid elements. It is so light, in fact, that it can float on water, though it would react quite vigorously while doing so. It is a soft, silvery white metal that can be cut with a simple knife, much like firm butter. This combination of being extremely lightweight and having a high electrochemical potential, its ability to store and release energy, makes it an unparalleled material. No other element can pack so much energy into such a small, light package, a quality that designers of portable electronics and electric vehicles find utterly indispensable. Because of these unique characteristics, lithium has found its way into a surprising array of applications. Its most famous role today is as the heart of the lithium-ion battery, powering everything from our smartphones and laptops to the electric cars that are reshaping transportation. But its utility does not end there. Lithium compounds are used to create high-temperature lubricants and specialized glass and ceramics that can withstand sudden temperature changes. In a completely different field, lithium carbonate has been a vital medication in psychiatry for decades, used to stabilize mood in patients with bipolar disorder, a testament to its profound and varied effects on complex systems. The journey of lithium from the Earth to our devices is a fascinating, if challenging one. The element is not found in its pure metallic form in nature due to its high reactivity. Instead, it is locked away in minerals and saltwater brines. The primary methods of extraction reflect these sources. One common method involves mining hard rock minerals like spodumene, which are then crushed and roasted at very high temperatures to extract the lithium. This process is energy-intensive and leaves behind significant amounts of waste rock, creating a considerable environmental footprint that must be carefully managed to avoid long-term damage to local ecosystems. A second, and increasingly prevalent method involves extracting lithium from underground brine reservoirs. These vast pools of salt-rich water are often found beneath dried lake beds or salars, most famously in the so-called Lithium Triangle of South America, which spans parts of Chile, Argentina, and Bolivia. The brine is pumped to the surface and into massive evaporation ponds. Over many months, the sun's heat slowly concentrates the lithium chloride in the water. This method is less energy-intensive than hard rock mining, but it consumes vast quantities of water in some of the most arid regions on the planet, raising serious concerns about its impact on local water supplies and the delicate ecosystems that depend on them. Once extracted and refined into compounds like lithium carbonate or lithium hydroxide, the element is ready for its primary application, the lithium-ion battery. Inside a battery, lithium ions are the charge carriers. When the battery is discharging, these tiny ions travel from the negative electrode, typically made of graphite, through a liquid electrolyte, to the positive electrode, which is often a metal oxide. This movement of ions creates a flow of electrons in the external circuit, which is the electric current that powers our devices. When we recharge the battery, an external power source forces the lithium ions to travel back to the anode, ready for the next cycle. The process is elegant in its chemical simplicity, but fraught with challenges. One of the main concerns is safety. The electrolyte used in most lithium-ion batteries is highly flammable. If a battery is damaged, overcharged, or exposed to high temperatures, it can lead to a dangerous condition known as thermal runaway, where the battery heats up uncontrollably, potentially causing fires or explosions. Engineers have developed numerous safety features, such as built-in circuits to prevent overcharging and vents to release pressure, but the inherent risk remains a subject of intense research and development, pushing scientists to find safer materials and battery designs. The insatiable demand for lithium has triggered a global rush, transforming the element into a strategic resource with profound economic and geopolitical implications. Nations and corporations are scrambling to secure a stable supply of what is often called white gold. This has led to a sharp increase in lithium prices and a surge in exploration and mining activities worldwide. Countries with significant lithium reserves, such as Australia, Chile, and China, now hold considerable influence over the global supply chain. This concentration of resources creates vulnerabilities, as disruptions in any of these key regions, whether due to political instability, trade disputes, or natural disasters, can have a ripple effect across the entire technology and automotive industries. This economic boom, however, comes with a significant environmental cost that cannot be ignored. The extraction processes, whether from hard rock or brine, leave a substantial mark on the planet. Hard rock mining generates large quantities of mine tailings and requires immense energy, contributing to carbon emissions. Brine extraction, while less carbon-intensive, consumes enormous volumes of water in arid regions, threatening fragile ecosystems and the livelihoods of local communities who depend on these scarce water resources. The chemical-laden evaporation ponds can also pose a risk of soil and water contamination if not managed with the utmost care, creating a difficult trade-off between our green energy ambitions and local environmental preservation. In response to these challenges, there is a growing emphasis on recycling lithium-ion batteries. Recovering valuable materials like lithium, cobalt, and nickel from spent batteries is not just an environmental imperative, but also an economic opportunity. It reduces our reliance on primary extraction, conserves natural resources, and helps create a more secure and circular supply chain. However, recycling these batteries is a complex and expensive process. They were not originally designed to be easily disassembled, and the variety of chemistries and formats makes it difficult to develop a standardized, efficient recycling method. Significant investment in research and infrastructure is needed to make recycling a truly viable, large-scale solution. The geopolitical landscape is further complicated by the fact that while some countries mine the raw lithium, others dominate the processing and manufacturing stages. China, for instance, controls a substantial majority of the world's lithium refining capacity and battery manufacturing. This gives it a powerful strategic advantage in the global transition to electric vehicles and renewable energy storage. Other nations, including the United States and European countries, are now actively working to build their own domestic supply chains, from mining to manufacturing, to reduce their dependence on foreign suppliers and bolster their own economic and national security in this new energy era. Looking ahead, the future of lithium appears to be as dynamic as its chemistry. The relentless drive for better performance is pushing researchers to move beyond the current generation of lithium-ion batteries. One of the most promising avenues of innovation is the development of solid-state batteries. These batteries replace the flammable liquid electrolyte with a solid material, such as a ceramic or polymer. This change could dramatically improve safety by eliminating the risk of fires, while also enabling higher energy densities. A solid-state battery could potentially store more energy in the same amount of space, leading to electric vehicles with longer ranges and smartphones that last for days on a single charge. Innovation is not limited to just solid-state technology. Scientists are also exploring new chemistries that could offer even greater performance. For example, lithium-sulfur batteries promise a theoretical energy density that is many times higher than that of current lithium-ion batteries, and sulfur is an abundant and inexpensive material. Another area of intense research is lithium-air batteries, which use oxygen from the surrounding air as a reactant, theoretically offering an energy density comparable to that of gasoline. However, both technologies face significant technical hurdles related to stability and lifespan that must be overcome before they can be commercialized. Beyond batteries, lithium's role in other advanced technologies continues to expand. It is a key ingredient in lightweight alloys used in the aerospace industry, helping to make aircraft more fuel efficient. In the field of nuclear energy, the isotope lithium-6 is essential for the production of tritium, a fuel for future fusion reactors, which hold the promise of generating nearly limitless clean energy. As we push the boundaries of science and engineering, the unique properties of this light and energetic metal will undoubtedly unlock new possibilities that we are only just beginning to imagine, solidifying its place as a foundational element of the 21st century. In conclusion, lithium stands as a quiet giant, a simple element whose atomic properties have unleashed a technological revolution. Its journey from cosmic origins to the heart of our modern world is a story of chemistry, engineering, and human ingenuity. While its extraction and use present significant environmental and geopolitical challenges that we must address with care and foresight, the path forward is one of innovation. From safer, more powerful batteries to its potential role in fusion energy, lithium will continue to be a powerhouse element, energizing our future and shaping the world of tomorrow in ways both seen and unseen.